In this video, we'll look at several more examples of how a differential equation can be used to model a physical system and how you might interpret the different models in terms of the equations that they represent. So the first example you want to look at is a chemical reaction. A plus C goes to B, and determine a model for how this reaction proceeds. So a lot of this here depends on the actual mechanism of this reaction. And that's something that comes out of your chemistry classes, your biology classes, your chemical engineering courses, things where you actually discuss how these reactions behave, what the actual mechanism is into how they work, and then what you can do with that to then write an equation for the rate of the reaction based on that fact. So for instance, if it's a simple reaction where like A plus B just collide and become C, then you might see something like the rate of change of C with respect to T, so how C develops in time, is some constant times the amount of A times the amount of B in this reactor. K here will be your rate constant, which is what it means in a differential equation point of view, but also what it means in the chemistry point of view, right? Your rate constant is the value K for which this is how it behaves. Now, if, for instance, you sort of need two A's to come together and then A plus B becomes C and there's some weird stuff going on there, you might see something instead like dc dt is K times A squared times B. General idea being the number of A's and B's that must come into contact to make this reaction happen is represented by the products or powers you see here. Because if you're thinking about it in terms of concentration, the likelihood of an A and a B coming into contact should be proportional to both the concentration of A, how many A's there are, and how many B's there are, because they have to collide to make this happen. So in general, a lot of these mechanisms are really sort of determined by looking at these equations. So you might write something like, I know A and B come together to make this happen. So let's say dc dt is going to be some constant K times A to some power and B to some power. I don't know what those powers are. And this is where this parameter estimation comes into play. I could run multiple experiments, get the data, and use that to figure out, in a best fit sort of way, what M, N, and K should be for this reaction given those circumstances. Right, I can then use the data and this estimation tool to figure out what should the power be here, what should the power be here, what should the coefficient be up in front here, and that can give me indication as to what this mechanism is going to look like. Because if I see it's just simple A, B, then it's probably some sort of collision reaction. If I see something more complicated, like A squared times B, then there's something weird going on with how these chemicals are interacting to produce this reaction. And I can use it to try to investigate more and figure out what's actually going on with how this behaves, based on taking data to best fit these parameters to the equation. And that's one way this can be useful. Another example is something like the Van Hoff equation, which basically illustrates how the rate constant K depends on temperature when you know things about the enthalpy of the reaction. And in this case, this here is separable, right? So I could solve it. It looks weird, but it is still separable, right? If I look at this the other way, I'll get that d natural log of K is negative enthalpy change over R times d 1 over T. So this all is a constant, it's just a coefficient here. So I can integrate this and get something like log of K is negative delta H0 over R times 1 over T, because integrating d1 over T just gives me 1 over T, integrating log of K just gives me log of K. And so I can just find K based on this stuff here. So K should be e to the negative delta H0 over R times 1 over T. And this could be used several ways. This could be a predictive thing where if I know what this enthalpy change is, I can predict how K is going to behave. I'll get a constant up here in front because I'll have a constant here. Or this can also be a best fit sort of model here. If I get data on how K depends on T, I could use that to back out what the enthalpy change should be for the reaction. This model can be used in both ways, and a lot of these models can be done this way. Depending on what data you have and what data you want, you can either use the model in a predictive way or in a constructive way. And that could be the same type of use here. Maybe you use one reaction to figure out this delta H0, and then go to another system to predict what K is going to be in that new format. And by constructive here, I mean that you can use it to help determine what parameters should be in different equations. Those are just two more examples of equations that come up in engineering contexts and how you might use them to talk about different parameters, different setups for these equations, use them in these fields to analyze what's going on under different circumstances.